Hi, this is a video for the Advanced Tire Physics course in the Rotational Motion and Astrophysics unit on linear motion and deriving the equations of motion and using calculus. These are the things that we will be learning about today, looking at calculus notation, deriving the equations of motion, and using calculus methods to calculate the instantaneous displacement, velocity, and acceleration. Let's start with a little recap from higher physics. So there we studied the equations of motion. At advanced higher, we do the same, but we use some calculus methods. If we look at an example of something being dropped and hitting the ground a certain time later, how could we solve this? So at National 5, you would have solved this using acceleration, speed, distance, time, and distance is the area underneath the graph, as shown here. So you could work out the speed when it hits the ground. You could plot a velocity time or speed time graph and then work out the area underneath the graph to work out the height, 5.5 meters. There was a number of steps there. Was there an easy way to do? Yes, you should be saying, because you know your way of solving it from higher physics. So we used 3 equations of motion in higher physics. For advanced higher, we now have to derive and using calculus to show where those come from. Let's firstly go through how we explained where they came from for higher. So we have the acceleration formula and that displacement is equal to the area. The first equation of motion was derived at from a simple rearrangement of A equals V minus U over T to give us V equals U plus AT. The second equation of motion, you didn't have to know this for higher, but we did go through it at the time. So the displacement is found by finding the area under the graph. So if we have a velocity time graph like this one, then calculating the area underneath the graph gives you the displacement. And at National 5, we did that by looking at the triangles and the squares. At higher, we did that using our relationship. So our displacement S is area 1 plus area 2. So area 1 is U high and T wide, the square, so it's U times T, because this side is length U, and this side is length T. Area 2 is V minus U high and T wide, and it's a triangle, so it's half times V minus U times T. Line 3 here introduces A, and that is because A is V minus U over T. So if we substitute in A times T for V minus U in this expression here, we can come up with this one there. And simplifying that, we get our second equation of motion, S equals ut plus half at squared, that we applied last year. Our third equation of motion is the one without the time, v squared equals u squared plus 2as. And really, you can come up with that by substitution. So we'll go back through this again because this is one of the methods that you can use at advanced higher to show where this is coming from. Okay, and we can use that to work out our speed that is hit at the bottom, for example. Okay, so there's an example on the right that uses this relationship. There is another equation that you can use. Because displacement is the average velocity times the time, S can be u plus v divided by 2 times t. And here's an example calculation of working out the distance in this way. So let's go on to looking at the calculus ways of doing this. So calculus is maths either invented by Newton or Leibniz. They both came up with the ideas very much at the same time, and this deals with quantities that are changing. So at higher, the equations of motion are for a constant acceleration. What happens if the acceleration isn't constant? It has a value at a particular time, but it's changing over time. So that's why we can use a calculus approach to provide us with a solution. Okay, there are two methods that you'll be aware of from your maths. Differentiation, and if you differentiate a function, that's the same as getting the gradient of that function if you're looking at the graph of the function, or you can integrate the function, which is the same as looking at the area underneath that graph up to that point. So the average velocity can be found by the change in displacement divided by the change in time. So we're using delta here. Delta's the change, means change in, and delta's where you've got a reasonably large change in displacement. To find it instantaneously, we consider a much smaller time interval, and so we need to look at the derivative of the displacement. So we reduce our time towards 0, and we get that v is equal to ds by dt. And you should be familiar with the differentiation notation, although most of the time you will have been looking at functions of y and functions of x. But the same principles apply. So if we look at acceleration, so what is acceleration? The rate of change of velocity, or the change in velocity divided by time. And the instantaneous acceleration is dv by dt. Because velocity is the rate of change of displacement over time, we can also write acceleration as the derivative of ds by dt, or which is written as d2s divided by dt squared. Okay, remember that velocity and acceleration and displacement are vectors. So let's summarize our three notations there. So velocity is the rate of change of displacement. We can write that mathematically as v equals ds by dt. Acceleration is the rate of change of velocity. We can write that as a equals dv by dt. And acceleration is the second derivative of the displacement, which means a equals d2s by dt squared. Let's think about gradients a little bit. So the gradient of a line is the rate of change of the line. Velocity is the rate of change of displacement. Acceleration is the rate of change of velocity. So here we've got some graphs on the side here. So we've got displacement time graph, the first one here. Okay, the gradient is positive. That's the velocity. And the gradient's increasing of the displacement time graph. So at this point, the gradient's quite small. At this point, the gradient's quite large. Okay, what we should do to really work out those gradients, if we wanted to do that, is we would draw a tangent. Can't find the straight line tool here, but we could draw a tangent to that line there and work out the gradient, and that would give us the gradient at that particular point. So here's our velocity time graph, and we can see that that's got a constant gradient, which leads to a constant acceleration that we've got. So the rate of change of displacement gives us the velocity. The rate of change of velocity gives us the acceleration. Okay, in some situations where the acceleration is not constant, the velocity time graph is curved, like this one. And so if we want to know how far this car has traveled in the first 10 seconds, we would need to work out the area underneath that graph. Okay, this is where our calculus methods come in, because we can see that this is not either a rectangle or a triangle shape. We can divide it into thin slices to do it, but we can use integration to do it better. Okay, so S, the displacement, is the integral of v, the velocity, with respect to time, between 0 and time t, which in this case would be 10. So let's have a look at how we derive the equations of motion using calculus. So acceleration is the rate of change of velocity. We've just said that that can be written as dv by dt. So if we rearrange this, we're looking at a time period from time 0 to time t. We can rearrange this so we get the integral of dv is equal to the integral of a times dt. And we've put limits on our integrals here. So we've got t and t equals 0 over here. And for the velocity, we've got v and we've got v equals 0, which we call u. Okay, now it's worth remembering that the a in this formula is a constant. So this is similar to you saying what would be the integral. Oops, I don't want to do that. What would be the integral of 4 times dy with respect to y and y equals 0, and the integral of 4 times dy, you should say to me, will be 4y between y and y equals 0. Okay, so the a is a constant, just like the numbers are constants when you are integrating in maths. So let's look at the next line here. So we've taken the a outside the integral because it's a constant, and then we're putting our definite integral brackets on, and if we integrate dt with respect to t, we get t, and dv we get v. Then if we substitute in the limits, we get v minus u, and over here on the left hand side we get at minus at when t is 0, and when t is 0, that is also 0, so that's why that wasn't shown in the formula there. And then we can see that is our first equation of motion. So we start with a equals dv by dt. We put the dt's on but different dt and dv on different sides of the equal sign. We add in the integrals, we add on the limits, and then we do the integration. So let's have a look at the second equation of motion and deriving that using calculus. So the second equation of motion is s equals ut plus half at squared. So this time we start with v equals ds by dt. So we then need to put the d's on either side of the equal sign and integrate. So that leaves us with the integral of ds is equal to the integral of v times dt, and we can add on the limits. Because it's a function of time, it's t and t equals 0, and s equals 0. v can be changed into u plus at because we know from our first equation of motion that that defines it in terms of as a function of time. We then use our square definite integral brackets, and on the left side ds integrates to s. On the right hand side u integrates to u times t. So we go from t to 0 to t to 1 divided by 1, which cancels out. And the next part we get half at squared because 8 is a constant, so that stays the same. The t is what we're integrating with respect to, and that power increases from t to the 1 to t to the 2, and then we divide by 2, and that's where the half comes from. And then we end up with our relationship that we're familiar with. The third equation of motion can be found in two different ways. I'll show you either of them, and it's up to you which one you prefer. Personally, I prefer the second one that I'm going to show you, and I find it a bit clearer to come up with mathematically. So, firstly, we'll notice that the last one, v squared is u squared plus 2as, doesn't have the time. So basically, we're saying instead of writing the time in our second equation of motion, we're going to substitute in v minus u over a. And that leaves us with this formula here. So we got u times t plus half at squared, where t is v minus u over a. So far, so simple. But then if you want to simplify that, it can get slightly difficult. So one of the things you can do is multiply all of those terms by 2a, because that means that you can get rid of these denominators, these dividing by a's, that are a pain in the neck for your multiplication. So then we end up with 2as is equal to 2u times v minus u. So the a has gone because we multiplied by 2a in this particular term. So we've cancelled it out. And in the second term, the same again. The half is gone because half times 2 is 1. And the a has also gone at the bottom because we've got a squared and we divided by a squared. We can then multiply that out, remembering how to factorize properly, v minus u all squared to get the right terms, and then we can simplify and rearrange. Okay, so that's how you show the third equation of motion. So let's look at the alternative way for the third equation of motion. Personally, I find this one a little bit more straightforward, but they're very similar. So this time we start with the first equation of motion, v equals u plus at, then we square that. Remembering that if we write it out like this, we get all the parts squared. Okay, then we're going to do some factorizing. So if we take out 2a from this term here and this term here, and we will then be able to see, hopefully, that this bit is the same as s. And we end up with our equation of motion. Okay, remember our other formula we can still use as well if we want to. So let's have a little summary. Velocity is the rate of change of displacement. We can write that using calculus notation as v equals ds by dt. Acceleration, a equals dv by dt, or d2s by dt squared. And a reminder on the right there that if we want velocity from displacement, we differentiate. If we want acceleration from velocity, we differentiate. If we want to go the other way round, we integrate. Okay, so let's have a look at some calculations here to show how do we actually apply this knowledge. So here's a problem. A tram starts from rest and we've got a relationship for the velocity of the tram. And we're asked to determine the acceleration after 20 seconds and the displacement of the tram after 20 seconds. Okay, so we want to work out the acceleration. So we should be saying the acceleration is the rate of change of velocity, dv by dt. So if I differentiate my function, I will end up with a function for acceleration. And then if I want my acceleration after 20 seconds, I can substitute in 20 and work out my acceleration. Second question asked us for displacement. We have a velocity function and we should say, v equals ds by dt. So if we want s, we need to integrate the function that we've got with respect to time. So we're going to integrate that function. Remember, t goes to t squared divided by 2. T squared goes to t cubed divided by 3. And then we can substitute in the 20 seconds to give us the displacement. Okay, let's look at a different example here of a particle. So this time we've got a cubed term. Find the acceleration after half a second. Acceleration is the rate of change of velocity, dv by dt. So we're going to differentiate the velocity function. And 4t cubed goes to 12t squared. We reduce the power and we get 3 times 4 to make 12. 5t squared. We reduce the power, so we get t, and we get 2 times 5 to give us 10. 6t goes to 6. And we substitute in our time to give us our acceleration. Okay, one more example. Space shuttles liftoff described by this relationship. This time it's the acceleration. Determine the velocity. So velocity is the rate of change of displacement, but acceleration is the rate of change of velocity. So we need to integrate. Looks quite confusing, but it's done in the same way. So we're integrating our function to get the velocity function. So we integrate that t cubed, t squared, t plus a number function. Okay, increasing the power, dividing by the power that we've increased to. And then we substitute in our numbers. Okay, let's have a look at our final example. A car brakes to a halt. The displacement is described by this relationship here. S equals 5.8 t minus 2.5 t squared. We're asked to draw a displacement time graph for the motion. So if we think about what that would look like, we've got displacement on one axis, s, we've got time on the other axis. So we be starting at 0. Where are we going to? Well, we need to know a time that it's going to take to stop, and we need to know the displacement, how far it's traveled, to work out that. Can we do that with that? Well, no, we need to know a little bit more from that. So we need to know how far it's gone when it stops. So at that point, the velocity is 0. So we need to know the velocity function. But that's okay because we have the displacement formula and we know that velocity is the rate of change of displacement. So if we do a differentiation of our formula, we can come up with the velocity term. So we differentiate it and we get 5.8 minus 5t. the 5 coming from the 2.5 times 2. What time does it take to stop? Well, when v equals 0, it has stopped. So if we solve that formula, we can work out the time and we get 1.16 seconds. So there's our time. Then we need to know, well, how far has it gone in that time? What is its displacement? So back to our original function, 5.8t minus 2.5t squared. Substitute in those numbers and we see it's gone 3.4 meters. We're then in a position where we can plot the graph because we have the 2 points. We might have to think about what it's going to look like between the 2 points that we've got, because we would have this point at the top on our graph here. We would have our 0 point down there. What's it going to look like in between? Well, it can't be a constant gradient, a straight line diagonally, because that would mean it's going at the same speed. So it has to be a curve. And then because it's slowing down, the displacement that's traveled every second as it slows down gets less. So we have to have this curve in that direction and not a curve in the other direction. Okay, and this is what's explained here. Okay, so we've got our different points. We know it's a curve. It's slowing down, so the curve has to be that way as opposed to being curved in any other way. So let's have a look through. We need to know calculus notation for rate of change. We'd have knowledge that velocity is the rate of change of displacement, acceleration is the rate of change of velocity, and acceleration is the second differential, ds by dt squared. Need to be able to derive the equations of motion using calculus, and you need to use those to carry out calculations. Okay, the last point is also looking at potentially equations of motion as well as calculus equations of motion. And these are the formulas that are on the relationship sheets that are provided to you.